Okay, so in this series of meeting for Crypto Club, we're going to introduce elliptic curve cryptography, especially the elliptic curve Diffie-Hellman key exchange. And in this meeting, we are going to introduce the definition of elliptic curve, as elliptic curve is a foreign definition for many of us here. So I'm going to introduce the definition first. We're going to cover some key concepts in the definition that we're unfamiliar with. The elliptic curve is actually a much more complicated thing than I thought. And I think we shall spend this whole meeting working on the definition. We're not going to go through everything about the elliptic curve. For example, we're not going to go through the projective geometry of elliptic curve. We're going to see what's happening, but we're not going to go into the detail. If any of us want to learn about the detail, please find a book and read. We're only going to introduce the concept that's relevant to our meetings, a series of meetings, the elliptic curve cryptography, and the projective geometry is not related, so we're not going to cover that in our meeting. Okay. Next, I'm going to introduce the Diffie-Hellman key exchange. I'm going to have a review of the Diffie-Hellman key exchange as we talked about this in our club meeting last year. We talked about the discrete logarithm-based Diffie-Hellman key exchange. And I'm going to introduce why we need the elliptic curve Diffie-Hellman key exchange instead of the discrete logarithm problem-based Diffie-Hellman key exchange. And we're going to go into the details about the mathematics behind it in the following series of meetings. Okay. So we have covered this last year. This Diffie-Hellman key exchange idea gives birth to the modern cryptography, the numerous encrypted message communications and transactions that's happening at this moment of time through the internet could all be traced back to the concept of public key exchange that is introduced in the Diffie-Hellman cryptographic protocol. So I'm going to fix one thing that's on here. So this G should not be the encrypted message, but the generator that is shared publicly in this system. So through the Diffie-Hellman key exchange, we could exchange key without letting Eve know when Eve does not have sufficient information for him to calculate what this shared key would be. So we're going to go through the concept. We're going to review it. So we have two parties, Alice and Bob. So Alice and Bob tries to communicate. So the key exchange happens between those two parties. And Eve is a person that wants to know what the key is. So Eve wants to decrypt this. Alice has a private key A, the lowercase a, and this private key means that Alice keeps this key to herself, and Bob has a private key B as well, and Bob keeps this lowercase b to himself. And through this public system, we have a very big prime P, which makes this problem difficult. And we have a generator G modulo P. And this generator is a common knowledge of both Alice and Bob and Eve, because this is generated by the system. And here we're going to see how Alice and Bob will share something that only they know, but not Eve. Okay, so Alice will compute the uppercase A is congruent to G to the lowercase a modulo P, and Bob will calculate uppercase B is congruent to G to the bth mod P. And Alice will send this uppercase A to Bob, and Bob will send his uppercase B to Alice. A and B. So now Alice could compute uppercase B to the lowercase a is congruent to something mod P. And Bob will be able to compute uppercase A to the B's, congruent to something mod P. And they should be equal to each other because we're only doing G to the A's to the B's, or G to the B's to the A's, which means they're the same. So then Alice and Bob will share something that both of them know, but Eve does not have a knowledge of. Why? Because this relies on the difficulty of the Diffie-Hellman, the discrete logarithm problem. It is really hard for Eve to solve for the lowercase a or the lowercase b, because Eve doesn't know the lowercase a and b. He couldn't decrypt the message and couldn't have the same thing that Alice and Bob shares. And this sort of Diffie-Hellman key exchange based on the discrete logarithm problem relies on two main assumptions. The first one is the Kirchhoff's principle. The Kirchhoff's principle, one quote from it, claims that one ought to design systems under the assumption that the enemy will immediately gain full familiarity with them, meaning that even though Eve knows this discrete logarithm problem and what's going on between the Alice and Bob, all the operations, he couldn't figure out what the message is, or what the thing that Alice and Bob share is, which is G to the A's to the B's. And the second assumption is the difficulty of discrete logarithm problem. And this sort of fulfills the first assumption. The first assumption claims that we need to design a very, very hard problem, that even we know what the problem is hard to solve. We have a variable prime P, which allows the Alice and Bob to be secured. Because it is very hard for Eve to compute what the shared message, what the shared thing Alice and Bob possess. And this discrete logarithm problem protects the countless communications or transactions from being easily attacked by the traditional computers. Here we claim that it is hard for the traditional computers to attack the system because they operate in linear time, but quantum computers operate in exponential times. They're much more faster than traditional computers, which means that if everyone has a quantum computer, this system is dangerous for us because people could decrypt the common knowledge possessed by Alice and Bob after the operations that they did through this platform. But the fact is, we all have traditional computers, but we do not have quantum computers. So our security is assured. One shortage of discrete logarithm problem is that it takes a long time for a computer to construct it. We're dealing with the traditional computers. It's time-wisely very inefficient for traditional computers to create such a problem. One thing that we should acknowledge is the value of time in our computational age. It takes a person 10 to 30 seconds to determine whether an article is interesting or not, to jump on or not. Which means if this problem takes a long time to compute, then our customer might not be happy with the results of this platform and might change a platform. We should design a system that allows us to compute things in a short time, to construct the problems in a short time, and also make sure that our users are secure using our platform. Then we will introduce this cryptography, this elliptic curve Diffie-Hellman key exchange to fulfill this. And it helps to reduce the running time and also the computation time for this whole process. Okay, so in this part, starting here and with our following meetings, we're going to see how elliptic curve cryptography an elliptic curve Diffie-Hellman key exchange actually operates. In this meeting, I want to go through the definition of elliptic curve. This definition is presented here. The geometry of this object is described algebraically by a set of solutions to the following equation over a certain field. So y squared is equal to x to the third plus ax plus b, where a and b are integers. An elliptic curve E over a closed field, meaning that x and y are selected from this closed field, is a non-singular projective curve of genus 1 with a marked point, a point at infinity, defined by the set union, E is equal to all the solutions for that equation and also the point at infinity. You might see a lot of concepts that you're unfamiliar with, so we're going to briefly introduce these concepts so we could get some knowledge of what it is. Okay. First of all, I want to talk about some basic identities that we might expect in the geometry of this shape. We're just going to take a shortcut here because it's very hard for me to show you the projective geometry of this object. We're just going to see the plot of this whole equation thing in a real field. So x and y are selected from the real number system. Two things that we're going to expect. One is about the geometry. One is about the symmetry. So we have y squared is equal to x to the third plus ax plus b. Then we might expect a symmetric shape here because we have y squared along the x-axis. The next is the intersection. So if we have a probing line, a random line in this real field, and then we move it to intersect with our curve, we will expect at most 3 intersections between the curve and the probing line that we have, which is the blue line shown here. The next concept that I am going to talk about is singularity. So the first thing that we might be interested to know is, where do elliptic curves come from? They come from the elliptic integral, which is associated with ellipses. If you would like to know more, you could definitely look it up. But we're just going to go from here. When we hear the term integral, we might think that each point on this curve should be differentiable. So we might speculate that this will be the definition for singularity, or at least associated with the definition of singularity. We say that an elliptic curve is different. It's not singular. Then we might expect this area point on this curve would be differentiable. Or in other words, in a geometric perspective, for any point on the elliptic curve, there is one unique tangent line that we could draw. Okay, so we're going to see some examples. For the first type, as we just saw in the decimal plot, we have 3 roots on here. So we have a closed curve on the left, and we have a hyperbolic shape on the right. We have 3 distinct real roots for this thing. So our equation could be written as y squared is equal to x minus r1 times x minus r2 times x minus r3. r1, r2, and r3 are different from each other, and they are all in the real field. the type 2, we could see a point here that is not differentiable. We could draw 2 tangent lines at this point. At this point with a marked arrow on it. And we could write this equation as the following. Y squared is equal to x minus r1. We assume that r1 is at minus 2. X is equal to minus 2. And x times x minus r2 squared. So the exponent above this x minus r2 term is also called multiplicity. So we have a repeated root of r2, which is at the point of the marked arrow. And the third type that we're going to introduce will be also not differentiable at the point here with the marked arrow. And this could be written as y squared is equal to x minus r1 to the third. So at this point here, at 0, 0, there is a repeated root of r1, and the multiplicity of that point will be 3. And we will expect this type 4, and type 4 is differentiable everywhere. We could draw a tangent line everywhere, a unique tangent line everywhere on a circle, on a curve. So we could write this equation in the following form. Y squared is equal to x minus r1 and an irreducible quadratic equation. We just speculated the singularity means we have a point that is indifferentiable, meaning we either have a point like type 2, the marked arrow in type 2, or is the point with the marked arrow in type 3. So the formal definition of singularity is on the graph, we have at least one singular point. The singular point in type 2 will be at the repeated root of R2. And the singular point in type 3 would be at the repeated root of R1. So another interpretation of that, or the name for these types, the second type has a singular point at the node, which is the marked point there. And the third type has a point at 0, 0, which is known as a cusp. So in the definition, we claim that our elliptic curve should be non-singular. It should be differentiable everywhere on the curve, which means we either have type 1 or type 4 for a basic shape of a real field. Here is an additional thing that I want to introduce, which is related to the singularity. What if we want a thing that would let us know whether this curve is singular or not? We could use the calculus concept of implicit differentiation to derive a discriminant for elliptic curve. If we do the implicit differentiation to our variable y in respect to x, we will obtain the following. Y squared is equal to x to the third plus ax plus b. 2y prime is equal to 3x squared plus a. And then gives us y prime is equal to 3x squared plus a divided by 2y. If there is a singular point, and this point is at x comma y, then y prime does not exist. This directs us back to a problem from primary school. 0 divided by 0. It doesn't exist. Then we shall derive 3x squared plus a is equal to 0. 2y is equal to 0. And we solve this system of equation. There are several ways for us to do this. And one way would be to use the Cardano's method to solve for x. This would be a possible way to do it. And we would derive something that is related to this. Or in the other way, we could just see that 27b squared plus 4a to the third is equal to 0. We could just replace this whole system of equation with this x to the third plus ax plus b. And since we have a is equal to negative 3x squared, we could replace this in this equation, which gives us b is equal to 2x to the third, which satisfies this equation down here. Or in this form, we could also derive things like that. Which gives us a discriminant. So for a graph to be non-singular, for an elliptic curve to be non-singular, we shall have 27b squared plus 4a to the third is not equal to 0. So here, I want to offer the singularity from another perspective, which is by using gradient. The gradient represents the direction of the steepest change. For example, on this graph, on the 3D diagram here, of course, this is not an elliptic curve, but we're just going to take a look at this diagram to get some sort of idea of what gradient is, as many of us might not be familiar with the concept. We could see that we have a lot of vectors, a lot of gradients that's pointing at this direction, and they are longer. They're sort of longer than the other ones. They're gathered in the middle here. And that represents they're changing faster than the rest because they're longer. And they are actually perpendicular to the original points on the 3D diagram here. It helps us to reduce the dimension from 3D to 2D, and we could observe the change visually by using this diagram. And what we are going to do to our equation of elliptic curve is that we want to change it to a contour map. We want to take the equation of the elliptic curve and change it to a function of the variable x and y. So we want to change this, set this equal to y squared minus x to the third minus ax minus b, meaning that we just want to move everything from the right to the left to obtain this. And when this is equal to 0, this is just one contour, for example, like that. That's not true, but I mean, say this is 0. We might have something like that, that's 1. That's 2. So this is the basic concept. For our original equation, we said this is equal to 0, meaning we only take this contour, but not the rest. And then we could figure out what the gradient is for this contour map. So we have del f x comma y. Del f x comma y, meaning that we're taking the gradient of that contour map. We're doing the following. For this equation here, we want to obtain a thing like that. So we want to take the partial derivative of fx and y in respect to x, and also the partial derivative of f in terms of y. I want to set this to 0 because inactive gradient would be the opposite direction to the positive ones, and 0 means there's no direction, which means it's undefined. So if we want the direction to be undefined, we set this to 0 to figure out the singular points on this contour map. And if we take the partial derivative, we're going to obtain something exactly like in the form of this equation here, this set of equation here, which gets us back to the same thing. Okay. The next concept that I am going to introduce is the concept of field. So a field is a set F with 2 binary operations, F times F mapped to F. So we have a Cartesian product here. We take any element from the set F and do an operation to it, and then we have any element from the set F, and then we obtain something. We map it by using a function to a element in the set F. And a field is defined with multiplication and addition, which satisfy the following 5 properties. The first one is the inverse. So for addition, we have a times minus a set equal to the identity element of 0. Identity element meaning that if we do operation on the identity element and one random element from the set, we're going to get the same thing. For multiplication, the identity element is 1. And the inverse will be a times b is equal to b times a is equal to 1. So we're going to find a and b in the set F. The commutativity is a plus b is equal to b plus a, or a times b is equal to b times a. Associativity will be a plus b, the sum of a plus b plus c is equal to a plus the sum of b plus c, or the product of ab is times c is equal to a times the product of b, c. The distributivity will be a times the sum of b plus c is equal to ab plus ac. So we're going to see that our real number system satisfies these rules. Complex systems satisfy these rules as well. And a complete residue, for example, for mod 5, that would be 0, 1, 2, 3, 4, also satisfy this. And we also have the natural number system satisfying this. And you're going to observe another fun fact, which is the real number system actually is part of the complex number system. We call this a subfield of the complex field. And the natural numbers are also a subfield of the complex system, the complex field or the real field, because they're part of it and satisfying all these rules. And we also have the same results for a complete residue. Here is the shape of complex field, the elliptic curving complex field. So the shape is called tora, and tora is of genus 1 because we have one handle or one hole in it. This is just showing you what the shape looks like. Here we have a finite field, elliptic curve over a finite field. We have some discrete point in it, and there is some sort of symmetric shape that we could observe in the diagram. And here is a projective space, the elliptic curve in projective space, and we're going to observe a point in infinity at the arrow here. We're not going into detail about the projective space, so if you're interested in projective geometry, feel free to read books about it. This is just showing you what it looks like. So then we go back to our definition. We sort of have an idea about what it is. Okay, so we know what the geometry looks like. We also know what a field is. So a closed field is when we have a polynomial with coefficient from a certain field, non-constant polynomial with coefficient from that field, then we have a root in that field. Meaning, if we look at these 4 types for elliptic curve in the real field, over real field, then we could see roots in that field that satisfy the definition. Okay, I'm going to go back to this. We know what non-singular is. We saw an example of elliptic curve in projective space. We have some idea about genus 1, which is the shape with one handle or one hole in it. And we see what the marked point O looks like. So we're done with the definition for elliptic curve. In the next meeting, we're going to talk about how the elliptic curve operates and how it connects with the Diffie-Hellman key exchange that we're going to introduce.